So our topic today is an application of derivatives, which is called related rates. This is when we have a rate of change of a given quantity and we want to find the rate of change of another quantity. A very basic example would be something like this. Let's say that we have the x and y are related through this equation. X squared plus y cubed is 56. And let's say that the rate of change of x with respect to time is 3. Now this would be units of x over units of time. So we want to find the rate of change of y when x is 8. So we start with the equation that relates x and y. And what we do is we differentiate it with respect to time. So with respect to t, implicitly. The derivative of x squared would be 2x times the derivative of x, which is dx dt. Plus the derivative of y cubed would be 3y squared times the derivative of y, because of the chain rule, that would be dy dt, equals the derivative of 56, which is a constant, so that is 0. Okay, so now we have an equation that has the two derivatives. Now the value of dx dt, we know it's 3. The value of dy dt is what we want to find out. We want to do this, we want this value when x is 8. Well, we still have the value of y that we don't know. But we have the equation. So using the original equation, we can find the value of y when x is 8. I'll substitute. That is 8 squared plus y cubed is 56. This yields that y cubed is 56 minus 64. That is negative 8. That's y cubed. So that means that y is negative 2. Now substituting this value into our differentiated equation, we get 2 times 8 plus 3 times negative 2 squared times dy dt. Okay, I made a mistake. I forgot here the times 3 because of the rate. It's equal to 0. So multiplying that, this is 2 times 8 times 3, that's 48, plus 3 times 4, 12 dy dt is 0, so dy dt is negative 48 divided by 12, which is negative 4. So the rate of change of y with respect to time when x is 8 is negative 4 units of y with respect to over units of time. Related rates problems, you will usually find them in applications. Let's put a simple one here. Let's say that we have a rectangle. In this rectangle, the length is changing. This is the length, and it's changing, so it's a rate of change. It's a derivative at 2 centimeters per minute. Okay, it's positive, so it's increasing. And the width, it's going to be changing at negative 1 centimeters per minute. Okay, it's decreasing because the rate of change is negative. So the question is, when the length is 30 centimeters and the width is 20 centimeters, how fast is the area changing? Okay, So we need an equation. We have two rates, and we're being asked for the rate of change of the area. This is dA dt. We have dL dt, we have dW dt, we want dA dt. So what we do is we find an equation that relates area, length, and width. Well, obviously that's the formula for the area of a rectangle. The area of a rectangle is length times width. And we differentiate it with respect to time. Okay, so the derivative of the area is dA dt. Now this is a product. So the derivative of this product is the derivative of L, dL dt, times W, plus L times the derivative of W with respect to time. Okay, in this case, everything else, we're being asked for the area. We know the rate of change of the length, we know the width, we know the length, we know the rate of change of the width, so it's just a matter of substituting the values. dA dt for this particular instance would be, that is 2 centimeters per minute times 20 centimeters plus 30 centimeters for the length times -1 centimeter per minute. Okay, so this gives us 40, that would be square centimeters per minute, plus -30 square centimeters per minute. So the area is changing at a rate of positive 10 square centimeters per minute. Okay, because it's positive, the area is increasing.